Hello, good morning everyone. I, Somojit Chatterjee, on behalf of my team, will present our paper detecting mobility context over smartphones using typing and smartphone engagement patterns. Before we start the actual presentation, I would like to spend a very little time on the background studies that motivated our research in this direction. As we know that in the context of mobility detection over smartphones, inertial motion sensors like accelerometer and gyroscope have been the key source of mobility information. This is further facilitated by the recent smartphone operating systems like Android and iOS, which provide permissionless access to these particular sensors. Although these sensors provide accurate mobility information to us, they also on the other side make us vulnerable to the breach of location privacy. This is mostly because of the fact that this accurate mobility information extracted from these sensors can be used to trace the location of a user. This risk is further escalated because of the fact that this accurate mobility information obtained from these sensors can be used to trace the location of a user even if he or she has explicitly chosen to turn off all the location services over their smartphone. Henceforth, the research problem statement that we pose here is that even if we drop the use of these IMU sensors from our smartphones, can there be any other alternate modality which can still give away enough information to detect accurate mobility context of a user? In this context, we find that typing as an alternate modality contains signatures for differentiating between various mobility contexts. This is mostly because our typing behavior changes across different mobilities. For example, when a person is walking, he might get distracted and thus may type slowly or make frequent mistakes in comparison to a person who is typing while he is sitting. Furthermore, previous works have also pointed out that there is a strong correlation between application usage and mobility. For evaluating these opportunities on using typing to detect mobility context of a user, we start by having a pilot study to analyze the typing data. But a major concern in this regard is collecting the data or collecting typing data for this purpose. So, we understand that data collection in this context is really challenging. To facilitate the data collection process for the pilot study, we develop an experimental apparatus to record or to collect typing data for the analysis. The experimental apparatus that we develop is nothing but an Android application with a custom keyboard and a ground truth collection unit. This ground truth collection unit uses Google Activity Recognition API for collecting activity levels. On the other hand, the custom keyboard has an inbuilt keyboard logger to collect the smartphone engagement data. All this data, including the ground truth, is dumped into a file storage which is then periodically uploaded by the smartphone app to a remote server. Now, coming on to the keyboard unit. The keyboard unit provides a regular QWERTY keyboard to the user. In this context, I would like to point out that we do not log any messages exchanged by the user while typing on this particular custom keyboard. Then what does the keyboard logger log? The keyboard logger actually logs several keystroke events like the application usage, the special key codes like @ spacebar, backspace, the pressure exerted by the user on the screen while typing, the velocity of typing in pixels per second, the tap duration for a single key press, and the inter-tap duration between two subsequent taps. Next, to perform the analysis and to collect in the while data for the pilot study, we needed an automated ground truth collection unit. To develop the automated data collection or the automated ground truth collection, we relied on the Google Activity Recognition API. This API returns 8 physical activity labels along with a confidence score. We use this confidence score to filter out noisy activity levels which usually have a lower confidence value. Now, with the data collected using the developed app, we perform the pilot study. The initial observation that we obtain from the pilot study is regarding the variation of inter-tap duration across different mobility contexts. From the plot, we can see that indeed there are significant variations in the inter-tap duration in different mobility contexts. So, it is comforting for us to know that indeed there are signatures for detecting mobility present in the typing patterns. However, on a closer look in the typing data, we also found that there are typing instances which can vary even when the user is in same mobility context. But why does this happen? On further observations and investigations, we found that there are factors like handedness which come into play. These factors like handedness are very subjective to a user and may differ from user to user depending on their ease of typing in a given mobility. Based on these understandings of the opportunities and challenges of using typing data for mobility detection, we developed a framework named ConType which can detect mobility context of a user from typing and smartphone engagement patterns. The process of developing ConType is as follows. We start by collecting the typing and smartphone data from the client application and upload it to a server. Once the data is collected, we first tackle the problem of handedness. As handedness is related to the ease of typing for a user, which in turn is very subjective, we choose to term this as modes of typing, namely the usual mode and the unusual mode. To resolve this, we simply use an unsupervised clustering approach based on two factors, the tap duration and the inter-tap duration. Now, once we cluster and find that the clusters are significant, then we choose to call the smaller cluster as the unusual mode for the user. Next, to extract relevant features from the typing instances, we need to sessionize the entire data into blocks. For this, we decide the session length by defining the term activity session length. The term activity session length simply means the duration of same ground truth mobility. So, if a user works continuously for 5 minutes, then the activity session length corresponding to that mobility context is 5 minutes or 300 seconds. Finally, we choose the session length as the minimum of all activity session lengths in the entire training dataset. Now, once the blocks in the typing data are formed, we extract several features. In the interest of time, I will be concentrating on some of the important features only. The first feature that we consider is the application usage. It is simply the most frequent application used in a session. Next, as we know that the mobility states like static, walking and in-vehicle are temporally related, therefore, the transition information can be helpful in pointing out the next probable mobility state. We capture this information by modeling the transitions between the different mobility states as a Markov model and then subsequently use it as a feature. Finally, we also use the typing mode as a feature. This is because the presence of an unusual mode may represent a particular mobility condition where a user is not very comfortable to type over smartphones. For example, a user may choose to type in an unusual way only when she is traveling on a very crowded bus. Thus, this typing mode can indeed be a very important feature in pointing out several different mobility contexts. Now, once these features are extracted, we use them to develop ML models that can detect three principal mobility contexts, namely the static, walking and in-vehicle. For this, we developed two versions of the mobility detection model. First one, the centralized model, which is based on random forest, and second, the personalized model based on both random forest and support vector machines. For both of these two models or two versions of mobility detection model, we perform a feature selection to choose the top 5 features. Next, we evaluate our proposed framework on an in the wild collected data. This data is mostly collected from the users who daily commute to their workplaces or universities. From the collected data, we observe that as most of the users do not spend equal amounts of time in each mobility context, there is a huge imbalance between the ground truth mobility classes. To fix this and evaluate our framework in a principled way, we balance the training data using SMOT and use it for training the models. Next, from the evaluation, we can observe that although all the models have almost similar median accuracy, the centralized model fails to capture the personalized typing signatures for a few users. Although this is to be realized that the centralized model is more realistic as an adversarial framework where the model is trying to sniff the mobility context of a user from his or her typing patterns. We also observe that almost 88% of the users have both the usual and unusual modes of typing modes present in their data. However, as a feature, typing mode appears only for 8% of the users. This is mostly because of the small volume of data for the smaller cluster, that is the unusual mode. We investigate the energy footprints of capturing an alternative modality like typing data for mobility detection. We observed that typing data can actually sniff the mobility of a user much stealthily in comparison to the IMU based approaches which have much higher energy footprints. Finally, we can conclude that we identify typing as an alternate modality for detecting mobility context and subsequently develop the framework ConType, which can sniff mobility from keystroke patterns. And for this, ConType does not require IMU data for mobility detection. At the end, we would like to express our gratitude to Dr. Lama Nachman and the reviewers of our paper. We would also like to thank Tata Consultancy Services for supporting our project throughout, the PerCom Student Travel Grant Committee, Microsoft Research Travel Grants Committee, ComSnets and LRN Association for providing travel grants. Thank you.